So let me recall what we did last time. Last time we did U1 gauge theory. We started with a set of matter superfields. Phi L, chiral superfields, so they are functions of y and theta. First component phi L, fermionic partners psi L of y, and the auxiliary field F. And we couple that to a vector superfield. With components A mu, fermionic components lambda, and an auxiliary field d of x. This is in Wess-Zumino gauge, superfield in Wess-Zumino gauge. We constructed field strength superfield. It's a chiral superfield, W alpha minus 1/4 d bar d alpha of E. And its conjugate W bar alpha dot as 1/4 d bar alpha dot P. V is a function of x, theta, theta bar, but this combination is a function of y and theta only because it's a chiral superfield. Similarly, this is a function of y bar and theta bar. And component expansion of W alpha was first component lambda. W alpha is function of y and theta. First component is lambda y. Second component is single theta component is theta alpha d of y. And there is also one component is half sigma mu theta alpha of F mu, where F mu is the field strength. Y, and a 2 theta component minus I theta theta sigma mu d mu derivative with respect to y of lambda bar y, the alpha component, spinor component. Gauge transformation on the vector superfield X as V goes to V I lambda minus lambda dagger, where lambda is a chiral superfield, parameter superfield, a chiral parameter superfield. and lambda dagger its conjugate. And this acts on chiral superfields phi L exponential minus twice I G T L phi L lambda phi L, where TL is the charge, U1 charge of phi L, and G is the coupling, is U1 gauge coupling. And phi L dagger transforms as phi L dagger exponential 2I G TL lambda. Given how V transforms, if we construct exponential 2 G TL V, then this object transforms as exponential 2 pi I G TL lambda. Oh, this is dagger here. Lambda dagger minus E 2 G TL V exponential 2 I G TL lambda. This would make the combination phi L dagger exponential 2 G T L V phi L gauge invariant. Well, this transforms as phi L dagger exponential 2I G T L lambda dagger like this one, and exponential 2 G T L transforms as exponential minus 2 I G T L lambda dagger exponential 2 G T L V times exponential 2 I G T L lambda, and phi transforms as exponential minus 2 I G T L phi L, and that is, this factor is 1, and this times this is 1. So that's gauge invariant by construction. And not only that, W alpha is also gauge invariant, and so is W bar alpha dot are gauge invariant. So we can construct a Lagrangian density, supersymmetric Lagrangian density, which is 1 by 4 W alpha, take the F component of this object and then add Hermitian conjugate. W alpha is gauge invariant, so the square of W alpha is gauge invariant, and adding Hermitian conjugate makes it real. So this can be a piece of Lagrangian density. And this is a function of y and theta because it's a product of two chiral superfields. So after you write that, you put theta equal to 0 and theta bar equal to 0. That will convert y mu into x mu here, and Hermitian conjugate will be a function of y mu bar. That will come, so that this whole thing is a function of x. And to this we add phi L dagger exponential 2g TL V phi L. And that's also gauge invariant because that's what we have checked. So we can add this. And it's a real object on its own. This is a real superfield. This is a real superfield exponential. That's a real superfield. You multiply by phi dagger, that's still a real superfield. And you take the d term of that. D term is the theta square and theta bar square coefficient. You could add to this also some normalization, eta some coupling times the d component of vector superfield, because that would also transform under supersymmetry as a total derivative. So this, you could add this one also. Then you could construct a superpotential curly W, which is a function of all these superfields, a polynomial function up to the highest power phi cube for normalizable field theories, and take an F term of that superfield and Hermitian conjugate, and then take theta equal to 0 and theta bar equal to 0. That will make it a function of x. Now, W phi, this curly W phi, is a polynomial in F. Every term has to be gauge invariant. That is, if I have a 2 phi term here, phi L k, this can be gauge invariant if is gauge invariant if TL, the charge of the phi L and charge of phi k add up to 0. Or if you have a term with the cube is gauge invariant if TL, Tk plus Tn is 0. So that would be the most general supersymmetric Lagrangian density for a U1 gauge theory. So now we know how W alpha is written in terms of components, we know phi how is written in components, we know how V is written in terms of components, expand it in terms of components. So U1 gauge theory in component fields will be given by Lagrangian density 1/2 d square plus minus 1/4 f mu nu square minus I lambda sigma bar dot d mu lambda bar. Sigma, this is a shorthand notation for sigma bar mu d mu. That would be these terms would come from W alpha F term plus Hermitian conjugate. This exercise we have done. Well, in that exercise I wrote it I by 2, this and plus an I by 2 conjugate of that. The two differ by a total derivative, so I have added them and thrown away a total derivative piece. So you will find that the earlier exercise, I think we had put it by half of this plus half of its conjugate. Then next, what we have here is d mu phi L mod square plus FL mod square, the auxiliary field in the phi L mod square d mu phi. This is covariant derivative d mu phi. This is gauge covariant derivative. Plus minus psi L sigma bar d. No, I think I have bars wrong, right? This bar should be on this. This should be here. Covariant derivative of psi L. That's right. And gauge covariant derivative on psi L is d mu psi L plus I g T L a mu psi L. So this is what we have. If we did not have this interaction, we would have had these pieces with the ordinary derivatives. What this interaction has done, by inserting this, it converts the covariant derivative or charge fields, ordinary derivatives or charge fields to covariant derivatives. In addition, it also has a term minus root 2 GTL phi L star lambda psi L plus phi L lambda bar psi L bar plus GTL phi L star phi L D. And that comes from the interactions of V and phi's. So this object would come from phi L dagger exponential 2GTL phi L D term. And then we have this term that gives you eta D. D term of V is D. Then we make the expansion of these objects, and the expansion of these objects is given by superpotential written as a function of the smallest component, the scalar field phi L, theta-less component, and L, take the derivative of superfield potential here with respect to phi L and call it curly omega phi WL phi L. That is this times auxiliary field of that supermultiplet minus half omega L K psi L psi K, where second derivative of the superpotential with respect to scalar fields phi K is what we call WLK phi L, or maybe phi. Just put it. And then Hermitian conjugate. So that would be our, and this term comes from, this term comes from F term of superpotential. Yeah. plus Hermitian conjugate. So this would be the most general U1 gauge invariant supersymmetric Lagrangian. Notice for the charge field psi L fermion, there is a gauge covariant derivative here. For phi L, there is a gauge covariant derivative here. But there is no gauge covariant derivative here. There is ordinary derivative. That's because gaugino is a superpartner lambda of the gauge field is chargeless. There is no charge. It's a chargeless, massless Majorana field. So this is a chargeless, massless Majorana fermion. Now let's take a special case of this most general theory. Special case. And this special case is supersymmetric QED. Yeah, before I do that, let me also remind you that what are the equations of motion that come from here for the constrained fields. So, auxiliary fields are FLs and Ds. They have no kinetic energy pieces. Other fields have kinetic energy. Photon has a kinetic energy piece. Photino, gauge field has a gaugino has kinetic energy piece. Charged scalar fields have kinetic piece. Their charged fermionic partners have kinetic energy piece, but F and D don't have. So they are auxiliary fields. If one wrote down the equations of motion for auxiliary fields, FL star is minus first derivative of the superpotential, which we also call in shorthand WL. That is straightforward from here. Vary with respect to F, you will get FL star here, and vary with respect to F here, you will get WL. And then vary with respect to D, get D is minus eta minus G TL phi L dagger, phi L star, phi L. Vary with respect to D here, you will get 1D from here, variation of D square is D times delta D, 1 from here, and 1 from eta, and 1 from this coupling. So that gives you the D equation of motion. And now if you put it back into this Lagrangian and construct the potential function, means collect non-kinetic energy terms and non-fermion couplings, which means you collect this term, this term, this term, and this term, and use those equations of motion, then the potential becomes simply sum over FL mod square plus half d square. And that's positive, that is non-negative. This is non-negative, because sum of a positive quantities, mod square of any quantity is positive, d is a real field, square of d is positive, sum of positive things. Non-negative as it should be expected in a supersymmetric theory. So now let's specialize this to a special case, a supersymmetric QED. Supersymmetric QED is made up of two chiral superfields. Call it phi plus, with components small phi plus, fermionic component psi plus, and auxiliary field F plus, and phi minus y root 2 theta psi minus theta theta F minus. Plus and minus reflect to the charges with electromagnetic charge or electrical charge. Plus and minus 1 unit. U1 gauge transformation will act on these. The phi plus superfield will go to exponential minus 2i E. E is the electromagnetic coupling, times the charge of phi plus. Charge of phi plus is 1 unit times this transformation parameter and phi minus will transform as minus 2i lambda times the charge of phi minus, which is minus 1, so it will become plus, so that's how under U1 gauge transformations these two objects will transform. Then we introduce the vector superfield as it is and construct the Lagrangian density. So Lagrangian density of super QED. So supersymmetric QED, SQED. By the same rules is W alpha, F term plus Hermitian conjugate plus phi plus dagger exponential 2 G 2 E V phi plus. There is some and for phi minus exponential minus 2 E V phi minus. the electromagnetic charge of phi plus is plus 1 unit and of minus is 1 minus unit. So that's the sign. And take the d term of this. So that's the same thing. Huh? Some dagger. This one should be dagger. So that's this one object. We don't put any eta. In super QED, we don't have eta. Eta is 0. So we don't have this term. Then we have the superpotential term. Now we take a special superpotential. Take the superpotential of phi plus and phi minus to be simply m times phi plus and phi minus. So therefore you add m phi plus times phi minus and take the f term of that and Hermitian conjugate. So that is the supersymmetric QED. Now supersymmetric QED describes a theory of photons and electrons. A massive electron, Dirac electron is a massive electron. And in our notations, Dirac electron, call it by some capital name psi d, is made up of, in our two component notation, psi plus alpha, or alpha down, and psi bar minus alpha dot up. The four components of the electron field are psi plus upper two components and psi minus bar. So that charge of psi plus is plus 1, psi minus is 1, minus 1, but psi minus bar is plus 1. So both these components have electrical charge plus 1 unit. Of charge plus 1 unit. Now let's see how does this look like in component fields. Component fields. L super QED. From the first piece, we have, we can write it in the long hand like this. So we'll have a piece like that. But we could eliminate all the auxiliary fields, and I write the answer after eliminating all the auxiliary fields. So we have minus 1 by 4 f mu minus I lambda bar sigma bar d dot lambda minus I psi plus bar sigma bar dot covariant derivative of psi plus minus I psi minus bar sigma bar covariant derivative of psi minus, where covariant derivative, this is gauge covariant derivative of psi plus gauge covariant derivative is d mu psi plus I times E a mu psi plus, and for minus this changes sign, because in the covariant derivative charge of the field that it acts on sets, and similarly covariant derivative on charge scalar fields is d mu phi plus minus I E A mu phi plus minus. So that is the kinetic energy piece for these objects. And then plus covariant derivative of phi plus mod square, covariant derivative of phi minus mod square. The kinetic energy for phi plus and phi minus. Then there is the mass term which comes from the superpotential, this superpotential. And the mass term is m psi plus psi minus plus psi plus bar, psi minus bar. And then the Yukawa coupling, root 2e lambda bar psi plus bar phi plus minus psi minus bar phi minus plus lambda psi plus phi plus star minus psi minus bar phi minus star. This is these Yukawa couplings in this theory. Then we have eliminated the auxiliary fields, we have the potential. And potential is m square phi plus square m phi minus square phi plus square and minus e square by 2 square mod phi plus square minus mod phi minus square whole square. So let me write the potential again. This comes after eliminating the auxiliary field. And as expected, this is also non-negative. Sum of positive quantities. This is positive, this is positive. This term tells us that phi and phi plus have mass m. This term tells us that psi plus psi minus together, I wrote somewhere Dirac fermion, make a Dirac fermion of mass m. This is the mass term for a Dirac fermion in two component notation, with upper component psi plus and lower component psi minus bar. So this is the mass term of a Dirac electron. So what do we have? The field content of this theory. A gauge field, a photon given by the gauge potential A. Its chargeless, massless fermionic partner and we give it a name 14O, represented by lambda here, is a Majorana fermion. A charge a Dirac electron with its left-handed component given by psi plus and right-handed component by psi minus bar. Of mass m. And then their superpartners two complex scalars phi plus and phi minus of mass phi plus and maybe if you say phi minus star of mass m and charge plus 1. And this Dirac fermion was of charge plus 1. Superpartners are the same charge, same mass. And you can give a name to it, call it scalar electron or S electron. That's one observation. Second observation is that look at this action. This Lagrangian has Yukawa couplings. Couplings between fermions and scalar fields. That's what we call Yukawa couplings. Couplings between fermions and scalar fields are called Yukawa couplings. So, supersymmetric generalization of QED has Yukawa couplings, fermions and scalar field, fermions and scalar field, and the conjugate. But what's interesting is that the strength of the Yukawa coupling is the same as electromagnetic strength. Strength of the Yukawa coupling, Yukawa terms, is given by electromagnetic coupling. Not only that, it also has 4 scalar interactions, mod phi square, square and the whole square. So it is 4 scalar couplings. Also, 4 scalar couplings are given in terms of electromagnetic coupling. E square. So though it introduced both Yukawa and four scalar couplings, but these couplings are not independent. Their strength is determined by electromagnetic coupling. In the general field theory, you could have them independent couplings, but here they are not independent, and that is the sign of supersymmetry. Supersymmetry links the couplings and masses of all partners in a supermultiplet. They have the same charges, same couplings, same masses in a supermultiplet. Okay, so is that okay?
So does this mean that at the particle for this it will not have any divergence?
It will have divergences. Okay. It won't have quadratic divergences. It will have logarithmic divergences. Okay. It will have beta function, but beta function for Yukawa, beta function for phi 4, and beta function for gauge theory will all be same. Gauge coupling. Gauge coupling is the coupling of A mu here to charge fermions, charge scalars. So the beta function for this coupling, a renormalization of this coupling, E square coupling, and Yukawa coupling here will all be same. Same in the sense of E square will have square of E. I mean, they'll be all related. E square will go as square of E. So that's our completes our elementary discussion of scalar QED. Now let's generalize it to non-abelian theory, because finally we want to write a supersymmetric theory for standard model, the interactions we know. So non-abelian generalization. So think of a gauge group, some gauge group G. It could be SU2 of electroweak theory, it could be SU3 of QCD, or any other gauge group that you want. And a set of a superfield, a chiral superfield capital phi in some representation given by the generator matrix TA of the gauge group. A representation in the gauge group is described by the generators. So phi will have certain number of components, and those objects will transform under gauge transformations corresponding to the charge given by TA, where the generators TA in a non-abelian theory satisfy a commutation relation. F, A, B, C are the structure constants. So you could think of phi, you could think of G to be an SE2 gauge group, then phi could, let's say, could be in a doublet representation of that. So phi, superfield phi would be made up of two components, and the corresponding representation matrices in that would be polymatrices sigma by 2 that we have learned, and they'll satisfy this equilibrium, where FABC corresponding to SU2 will come here, which is ordinary epsilon ABC. Or if you have an SU2 and you take phi to be in its triplet representation, then you would have a corresponding set of generators, 3 cross 3 matrices, 3 of them, A will run into 1 to up to 3, that's the dimension of the group SU2. So 3 cross 3 matrices, and those will satisfy this algebra. Or you could have any arbitrary representation. This property is true for all generators of the group, for the this property, that they follow this commutation relation, and this FABC symbol constant characterizes the group or algebra of the group generators. In addition to that, there is also a group theory object called trace of A and B, trace of T A times T B. This for a representation is K times delta AB, where K characterizes the representation. K is the characteristic of the representation. So if you change the representation for phi, the K will change. K is a representation dependent. For example, in SU2 case, in fundamental representation, K is half, I think. Is that right? That's how trace of sigma by 2 is half. If you have a triplet representation, then K is, I think, 1. So K characterizes the representation, FABC characterizes the group. Now, how does the superfield transform under gauge transformations? Gauge transformations. For gauge transformation, introduce chiral parameter superfield and also in this way TAs are Hermitian matrices. This is important. This with an I here, they are Hermitian matrices. So introduce a chiral superfield parameter lambda A. And A runs from 1, 2, 3, 4 up to the dimension of the group, which means it is in the adjoint representation. The number of independent A's is the same as number of independent T's, which is the same as number of independent gauge fields. Construct a matrix valued parameter superfield, call it lambda twice, G is the coupling, TA lambda A. So multiply it by TA, which is the representation matrix of phi. TA are representation matrices of phi. So now it's a matrix valued superfield. These are number of superfields multiplied by TA. TA is a matrix, so it's a matrix valued superfield. 2G is some convenient normalization. G is the coupling. In most ordinary gauge theories, you don't put this, or you put at least G. This 2 is with something special to this construction, because if you put 2 here, then factors become easier in the later calculation. And then conjugate lambda dagger, which is 2G TA lambda dagger A. These are chiral superfields. What does chiral superfield means? That d derivative, super covariant derivative of this object bar is 0. That is chirality condition. And d alpha of lambda dagger is 0, anti-chirality. So now how does phi change? Superfield phi. Exponential minus I lambda on phi under gauge transformations. And conjugate superfield dagger conjugate of that. See, the order. This is on the left, this is on the right, because now these objects are matrix valued. They're matrix valued. There is a matrix acting, and these are vector. It has a number of components. X on this. So this is the phi dagger. Now next, introduce vector superfields. VA in adjoint representation of gauge group for SU2. There will be 3 of them. A will take values 1, 2, 3. For SU3, A will take 8 values, 1, 2, 3, up to 8. And just to remind ourselves, in component of in the Wess-Zumino gauge, components of this V field are theta sigma mu theta bar A mu A plus theta 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 bar lambda bar A x x plus theta bar theta lambda A x plus half theta 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 bar dA of x. So the gauge field in the adjoint representation, fermionic partners, fermionic partner in the adjoint representation of the gauge group, and its conjugate, and auxiliary field in the adjoint representation of the gauge group. So let me write in words: A mu lambda dA in adjoint representation of gauge group. Now from this, construct a matrix valued vector superfield V 2G TA VA. VA were vector superfields, which means real superfields. Dagger of VA is same as VA. This is a matrix valued real superfield. V dagger V is same. Now under gauge transformation, construct exponential of V. You remember exponential of V we learnt earlier for abelian theory. Because of that way V is defined in terms of thetas, written as a series, it truncates. There are no more terms. So this exponential transforms to exponential of V prime by I lambda dagger E V I lambda. Now let me check the signs. This is minus. This is simply the non-abelian generalization of how exponential V transformed in the U1 theory. Except that now they have become matrix valued. V is matrix valued, so E to V is matrix valued. This is matrix valued because lambda is matrix valued. Lambda is matrix valued. Now if E of V transforms like this, what about E of minus V? Is that clear? E of minus V is the inverse of this. Just take the inverse. Inverse, you just go from this order. Take a minus, minus, minus. Or check, take the product of this. This times this is 1. Take the product. This times this is 1. This is 1. This is 1. Now this is how we have given now transformation properties of phi. We have given transformation properties of this exponential of V. Now it's straightforward to check how does a phi dagger EV phi dagger transform. Phi dagger transforms as exponential I lambda dagger. EV transforms as exponential minus I lambda dagger. EV exponential I lambda. And phi transforms as exponential minus I lambda phi. This is 1. This is 1. Gauge invariant. So we have already a possible term for the Lagrangian density. It's a gauge invariant object. It's a real superfield. So I can take the D term of this. That will give me a possible term for the Lagrangian. But I also need the field strength part of the Lagrangian. So construct field strength superfield. Ordinary W alpha minus 1/4 d alpha exponential V exponential minus V d bar. D alpha on exponential V multiply by d minus V and take d bar square of this. If V were a U1 theory, which means V is not a matrix in U1 theory, this is exactly how we had defined it for U1 theory. D of exponential V is V times exponential for U1 theory. So exponential will go away. This is how we define. So this is a supersymmetric generalization. And conjugate Now, how do these objects transform under gauge transformations? This is a matrix valued, these are matrix valued objects. So, therefore, it is a matrix valued superfield. You can check it, it's a, for the same reason, it's a chiral superfield. You can check it if you check, let's check. Chiral super means that d bar acting on this must be 0. That is product of 3 d bars. For the same reason we said product of 3 bars is 0. So this is by construction a chiral superfield, and this is by construction an anti-chiral superfield. But under gauge transformation, how do W's transform? Exponential minus I lambda W alpha exponential I lambda, and the conjugate this is how they transform. W alpha with exponential I lambda on the right, exponential minus I lambda on the left. W bar alpha dot with exponential I lambda dagger on the right minus I. It's easy to check that these are the gauge transformations. Let's verify. So W alpha goes to W alpha prime, and W alpha prime is 1 by 4 d bar exponential V prime d alpha V prime, and that is minus 1 by 4 d bar, and what is this object? We gave the transformation law for V. V inverse is exponential I lambda E minus V exponential I lambda dagger. That is this object times d alpha exponential I lambda dagger EV exponential I lambda. Is that right? This is what this is, and this is what this is. Now notice lambda dagger is an anti-chiral superfield. D unbarred acting on lambda dagger is 0. So I can take it across here because this object acting on lambda is 0. So that means I can take it across. That phase will kill this phase. So what we have used the fact that d alpha on lambda dagger is 0. Next, this is also true, d bar on lambda is 0 because it's a chiral superfield. This is an anti-chiral superfield, it's a chiral superfield. So I can take this phase across these. Let me write one more line here. Now let me write this now as I lambda d dagger EV d alpha on EV EI lambda. Now this d alpha acts on what is everything on the right. So it acts on EV in particular one piece. So I just wrote that. Then minus 1/4 EI lambda d dagger exponential minus V exponential V d alpha EI lambda. Is that clear? By putting this bracket, what I mean is that this operator is acting only on this. And when it acts on this piece, that's an extra piece. So I pull this out. Now what is this? This object is exponential I lambda W alpha I lambda. This is E, V and E exponential minus V, so this is 1. So W alpha transforms to W alpha prime, which is E I lambda W alpha E I lambda minus. Now let's rewrite this object in the following way. 1/4 E minus I lambda d bar beta anti-commutator d bar beta d alpha exponential I lambda. Is that what it is? Now notice there was only one term there, that is d bar square times d alpha. I have introduced another term which is here alpha times d bar, but d bar acting on lambda is 0. So I haven't done anything wrong. D bar beta acting on is 0. So the extra term that I have added here is 0. But then this object, we know d beta dot d alpha anti-commutator is minus 2I sigma mu alpha beta dot d mu d mu from the algebra. Which means this commutator is essentially an ordinary derivative. Now d bar commutes with ordinary derivative. So therefore, I can rewrite this term as minus 1/4 EI lambda commutator d bar beta d alpha anti-commutator d bar beta dot EI lambda, but that is 0. So this is 0. So that tells me W alpha changes to W alpha prime, which is exponential I lambda W alpha exponential lambda. And similarly, you can check W bar transforms to W bar dot alpha exponential minus I lambda W bar alpha dot I lambda tagger. So now that I know transmission properties of the W superfield, let me now list. So then I can take trace of W alpha, that would be gauge invariant, because I will multiply these two W's, in between this will go away and trace will take away what is on this. So trace W alpha is same as trace W alpha, and trace W bar alpha dot is same as trace W alpha dot W bar alpha dot. So these are gauge invariant. So these are gauge invariant chiral superfields because they are products of chiral superfields or anti-chiral superfield. This is chiral superfield, this is anti-chiral. So I can take the D term of these objects, F term of these objects, and construct a piece of the Lagrangian. Now let me write W alpha. This is a matrix valued object 2G TA times W alpha A. Pull out W alpha superfield from this. Then trace of W alpha is 4G square K W alpha A W A alpha A alpha. K was that trace of TA TB is K times delta AP. So which means I could write trace this or I could write this in my action. And field strength superfield WA alpha or in component It's a straightforward calculation. The same way like we did it for the U1 theory. You can just do this for this non-abelian theory. First component is a chiral superfield, so it's a function of y and theta. First component is a fermion, theta alpha. Single theta component is an auxiliary field, dA, plus sigma mu nu theta alpha f mu nu a y. Now some factor, what is the factor? Plus half minus I theta theta sigma mu mu alpha beta covariant derivative of lambda a beta dot, where now f mu nu a is the non-abelian field strength. And covariant derivative of lambda is gauge covariant derivative. So this is what in the component field it is. This is simply, if you look at the U1 exercise, it's simply generalization of U1 to non-abelian. F gets replaced by F strength of the non-abelian theory. This gets replaced by the covariant derivative of the non-abelian theory. Here you had an ordinary derivative because lambda in the U1 theory was chargeless. But here it transforms as an adjoint representation, so you have the corresponding covariant derivative. Now, we don't have to do much exercise to write down what is the possible Lagrangian density. So, supersymmetric Lagrangian density. Take 1/4 WA alpha, WA alpha, F component of this. What WA alpha is that object? And add Hermitian conjugate to it. This is by construction gauge invariant. It's by construction under supersymmetric transformation. It transforms as a total derivative, and therefore the action is supersymmetric invariant. Plus phi dagger EV phi, because that's what we saw. There's a gauge invariant object, and it's a vector superfield. Take the D component. And this would be directly a function of x. Here you make theta 0 and theta bar to be 0, and that would make it a function of x. And then to this you may add some superpotential. F term of that and Hermitian conjugate. This would be also a function of x after you have put theta equal to 0 and theta bar equal to 0. So, for example, if you were to do supersymmetric SU2 gauge theory, so you would have the corresponding super field, field strength superfield square here, and if you have fields in doublets like in standard model of SU2, so you will have the fields in doublets, a certain number of them. I just took one of them, so if there are more, so you put an L there and sum them up. So now we know how to construct exactly a supersymmetric generalization of standard model. There will be more fields, many more copies, but the structure is going to be exactly this. Now, what does this look in components? This gives me 1/4 F mu nu A, F mu nu A, F mu nu minus I lambda A bar sigma bar covariant derivative lambda A minus, that is the gauge part, and this is the gaugino part, kinetic energy. Then the matter complex give me plus covariant derivative of phi L mod square. Now covariant derivative of phi L is gauge covariant derivative, gauge covariant derivative is d mu of phi L plus I G T A L L K A mu A phi L K. Now phi L is the number of components of scalar field phi, because in a representation it will have a certain number of components. So I have written those clearly. So phi scalar field X is phi L. It's a certain number of components, phi 1x, phi 2x, phi nx, depending upon the dimension of the representation. For a doublet there will be 2, for a triplet representation of SU2 there will be 3. So that's what this L is. Then the fermion piece. Now covariant derivative on lambda we have defined somewhere. Did we define it? There. Because lambda is a joint representation, that's how the covariant derivative on lambda acts. Covariant derivative on phi we have defined. Covariant derivative of psi L is d mu psi L plus I G T A L K A mu A psi K. So that's this piece. Then we have the Yukawa couplings, minus root 2 G lambda bar A psi L bar T A L K phi K plus conjugate Hermitian conjugate minus 1/2 psi L psi K superpotential L K plus Hermitian conjugate. So, superpotential L K is the second derivative of superpotential with respect to, and you take again, so this is what it is. So let me write it. Superpotential L K of phi is d phi L d phi K of superpotential of phi. And then minus V of phi L. Which is the potential. Again, we have eliminated the auxiliary fields. Let me write down the equations of auxiliary fields. Auxiliary fields. FL star would be minus superpotential first derivative, which is same as what we call FL, and D would be minus G phi L dagger TA LK phi K. And V would be phi L star phi L sum over L plus half D square. We don't have to do much exercise now because this is the structure that how it should be. Because we have always learned that the potential finally is square of the auxiliary fields of the chiral superfields and square of the auxiliary field of the vector superfield. Now this is, now let me write it, this is dA, dA. And this is non-negative. Is that fine? And again here, if you notice that Yukawa coupling and gauge coupling are not independent. See, these are Yukawa couplings, coupling two fermions and a scalar. Strength is same gauge coupling. Now in the potential also, if I take the four scalar theory, dA square is square of this object. There's two scalars, square of that is four scalar. Couplings again G square. So again here, Yukawa couplings and four scalar couplings are non-independent scale couplings. Which is again the reflection of supersymmetry. I think with that I stop today.